So first, welcome back. I hope we had a good weekend. I know you guys took the tests on Friday. Obviously, I wasn't able to be here, and I got the tests this morning at like 8:05. I have not looked at them, so I don't have them. There is a very good chance I will not have them for Wednesday. I'm going on a trip out of state tonight, and I'm busy all day tomorrow, and so I will do my best to get them back Wednesday, but I'm not optimistic about that. But certainly by Friday, I will have them back to you. And when I hand them back to you, I will give you a snapshot, an up-to-date snapshot of what your grade in this course would be if we ended right now. And it will incorporate your quests and your homework and your test grade. Okay, so today we cover two topics. First one is going to be pretty quick. It's the Pythagorean theorem. And the second one is laws of exponents. And I'll just point out that we're going to be talking about exponents over the course of several classes. Next class is integer exponents, then we talk radicals, and the next class you see the word exponents again. And so this exponents theme is going to be with us for several classes. But let's go ahead and start on the new packet again on page 3, and we'll begin up here at the top with the daily summary. Let's go to Virginia. Thank you. Casey, number 1. Okay. Okay, so let's, so we've seen this equation before, this a squared plus b squared equals c squared. It is certainly the most famous theorem in all of mathematics. And actually one of our former presidents proved this theorem. This theorem has been proven hundreds of times. And James Garfield was an amateur mathematician, and he supplied an original proof of this theorem. So let's take a look at number 2, Dan. Okay, thank you. So, so we've got this entertainment center, and it's got this big old space in it for our TV. And the entertainment center measures 17 by 21, that rectangle. And when you look at televisions, you will see exactly one measurement on them in terms of a distance, and it's always the measurement along the diagonal. So the TV isn't going to say it's 17 by 21. The TV is going to say it is a 27-inch TV. Any guesses on why the TV manufacturers advertise that single number, the diagonal, as opposed to the length or the width or both of those? Makes it look bigger. What's the biggest single line you could draw touching 2 points of that rectangle? It's the diagonal. And so the fact that they're advertising the diagonal is purely a marketing ploy. Can't really blame them. As Caleb points out, it's the biggest number they could find, so that's the one they're going to show us. So the question is, can we fit a 27-inch diagonal into this rectangle? So I'm going to draw it in here, and I'm going to we'll give it a name in just a second. But what we need to do is figure out the length of that red line, and then we'll compare that to the 27 inches that we're given. Okay, so in terms of Pythagorean theorem, basically it just says that if you square two sides of a triangle, of a right triangle, add them up, you should get the third side squared. Well, only if you're really careful. What needs to be true about that C? Which of the three sides is called the C? Is the largest. The one that's opposite the right angle is C, and so a real good name for that guy is C. So Pythagorean theorem says that 17 squared plus 21 squared is equal to C squared. We happen to have the perfect squares in front of us here in yellow. So how much is 17 squared? 289. So that one up there, 17 squared. And then 21 squared, everyone knows that. That's 441, right? You guys all know that, right? Yeah. And then we add them up. So what do we get here? 0, 3, 730. Great. And now for the first time this semester, I think this is the first time, we're solving an equation where the variable is squared. I'm pretty sure this is the first time we've done this semester. So we need to do the square root, not just of 730, but really the square root of both sides, right? It's like one of our fundamental things to do in algebra. As long as you do the same thing to both sides, you're probably fine. You want to add 5, just do it to both sides. You want to divide by 2, great, just do it to both sides. You want to take the square root, super, do it to both sides. So I'm going to actually do a step that many people skip, and that's to rewrite that equation in its entirety, and then put that square root symbol on top, right? And the reason we did that is because what's going to happen on the right-hand side? Yes, and what is the square root of c squared? It's c, that's the idea. So we wanted to get rid of that square. The square root is exactly the right tool. And then the square root of 730, we type into a calculator. Who's got a number for me? 27.02, approximately. So the length of this red diagonal is about 27.02 inches. So will our 27-inch TV fit into that space? Yes, just barely. Okay? All right, let's move on to number 3. And for number 3, let's go to Sam. Okay, so we all know that 7 squared is 49. What does that mean? It means 7 times 7. How do I know that it's 7 times 7? What about 7 squared says 7 times 7? As opposed to 7 times 7 times another 7. This is 5 to the 4th. It means 5 times 5 times 5 times 5. How many 5s? 4 of them. So that number that's up there is the exponent or the power, and it tells you how many times to multiply the number that's down below. The number that's down below is called the base. 2 to the 8th means 2 times 2 times 2 times 2, 8 of them all lined up next to each other, okay? So basic stuff about exponents. Some definitions down here, I just used the word base. The base is the number that is being repeatedly multiplied. So the base in these examples is 7, 5, and 2. And the exponent is the number that's up on top. Exponents are 2, 4, and 8. Definition, it doesn't really help much. I think the examples are clearer, but x to the n means you multiply a bunch of x's together. How many of them? N of them, okay? All right, so far so good, but things start to get tricky when we talk about laws of exponents. And maybe not so much today. I think the ones today are gonna be fairly straightforward, but then we're gonna see some new laws, and I think that they're gonna kind of get confused in with these first laws that we have. So let's make sure we're solid on these before we move on. I have put a little screen shadow over here, so if you could like cover that with your hand or just put a little piece of paper over it or something. I don't want us to look at those laws. First, I want to look at the examples. So the first example says 3 to the 5th times 3 squared. No, we're not looking for calculator stuff here. We're just looking to see if there's a way to mush those 3's together. So 3 to the 5th means you're going to multiply 5 3's together, yes? 3, 3, 3, 3, 3. And 3 squared means 2 3's right next to each other. And so now if you look at that whole long collection of 3's written out, you get rid of those parentheses and you'll say, oh, this is really 3 to a certain power, right? How many 3's are there? 7. And is there an easy way to know that there are going to be 7 3's without going through the hassle of writing them all out? Yes, as we add the exponents, right? The 5 plus the 2 gives you 7. And so that's this very first rule here. X to the m times x to the n is really x to the m plus n. 3 to the 5th times 3 to the 2nd. You just have 7 3's. Okay, so that's our first law of exponents. Okay, next example. 3 to the 5th over 3 squared. This is now a division problem. The first one was a multiplication. So 3 to the 5th, you write out 5 3's on top. 3 squared, you write a couple 3's on the bottom. What can you do with some of these 3's? You can get rid of them. You can cancel them, right? So I'll get rid of those, get rid of those. How many 3's are left over? 3. So it's really 3 to the 3rd power. And was there a way to know that there would be 3 3's left over looking at the 5 and the 2? We subtract them. Of course, you had 5 on top, 2 on the bottom. Those 2 will cancel, and you're left with just 3 left over. So that's our basic division becomes subtraction. Okay, next example says 3 to the 5th squared. And the question is there some nifty little thing we can do with the 5 and the 2 to figure out what this really is? The answer is yes, but let's go through the derivation here. So when you square something, it just means multiply it by itself, right? So we buy that that's 3 to the 5th squared, just 2 copies of 3 to the 5th. And then 3 to the 5th, you can just list out 5 3's there. And then the other 3 to the 5th, you can list those guys there. How many 3's do we have when we pull them all together? 10 of them. So was there an easy way to know that there were going to be 10 by looking at the 5 and the 2? It's multiplication. It's 5 times 2 because you have 2 copies of 5's. So that's our next rule there. Is an exponent raised to an exponent. We get to multiply those exponents. Next one, if you have 2 things multiplied in parentheses and then raised to a power, so 3 times 4 to the 3rd power. Sure, 3 times 4 is 12, but that's not what I'm after here. I'm looking for a rule that applies to any kind of exponents. So don't get caught in the arithmetic. So 3 times 4 cubed, we can just write 3 copies of that thing, right? That's what it means to cube something. And now this is straight multiplication, and we know that we can multiply numbers in any order, right? Like 3 times 4 is the same as 4 times 3. Yes? So then all we're going to do is shuffle these things around. The parentheses are meaningless. They're not necessary anymore. So we're just going to regroup them. We're going to put all the 3's in the front and all the 4's in the back. So would you guys agree that there are 3 3's multiplied and 3 4's multiplied? And then 3 3's in shorthand is really 3 cubed. And then these 4's is really 4 cubed. And so we look at this original guy and then we kind of skip all the middle stuff and get to the end. And in some sense, think about that cubed power coming in and going on top of each of the guys in the parentheses. 3 to the 3rd times 4 to the 3rd. Some people look at that and think of it as like a distributing, like the cubed on the outside distributes. I'm not going to use that word because distributing means something very specific, and it isn't this, but it does look kind of like distributing. Okay, and then the last example in this chart is like the same example, but instead of having 2 guys multiplied in the parentheses, we're going to have them divided. Okay, 3/4 cubed, we just put 3 copies of 3/4. And then how do we multiply fractions together? Do we need a common denominator? How do we multiply fractions? We just go straight across, no common denominator needed. So we go straight across, 3 times 3 times 3, that's upstairs. 4 times 4 times 4, that's downstairs. So upstairs is 3 cubed, downstairs is 4 cubed, and the goal is to be able to look at that guy and just jump straight to this one. And we say, oh sure, I can kind of imagine that 3rd power coming in and hitting both of these guys to give us our final answer. So I think those are both illustrated in the bottom 2 rows there. Okay, so lots of rules about exponents. I'm hoping that looking through this chart like we just did will convince you that the rules are reasonable. And then finally, one more rule that we're going to look at now, and it's number 5. It says, in addition to the 5 laws of exponents we just reviewed, there are some other properties of exponents. Your book makes this distinction between laws and properties. I don't make that distinction. I don't need you to either. So here are 2 of them. We're just going to look at the first one for right now. A to the 0, it turns out any number to the 0 power is 1. If you have a calculator on you, real quick, see if you can type in like 17 to the 0 power. And if you don't know how to hit the exponent button on your calculator, I can show you in a little while. But it should tell you that the answer is 1. So why should it be reasonable that the answer is 1? Okay, let's suppose that I had this, 3 to the 5th over 3 to the 5th. What does that equal to without doing any arithmetic? This is definitely equal to 1, right? Without even knowing how much 3 to the 5th is, this is clearly equal to 1. But we have a rule that we just looked at on the previous page that said when you have 2 guys right here divided by each other, what can you do with the exponents? This was the very second row in our table on the previous page. What do we do with these exponents? We subtract them. That's what it said. This is the second row in that table. And so if we subtract them, then what do we get as the power? 0. And so if I want that second row rule to apply, and I sure do because it seemed reasonable, then I have no choice but to define 3 to the 0 to equal 1. Because I know the answer to this problem is 1, and 3 to the 0 somehow is also the answer, so it better be the case that we call 3 to the 0 1. If the numbers aren't the same, then we can't do it. Yeah, that's a good observation, Jasper, is that these guys had to be the same for us to use that property in the table. Okay, we're going to skip the second property in this table until next class and just jump down to number 6. Let's go to Jasper for 6. Mm-hmm. Okay, 3 problems right here. -4 squared, -4 squared, -4 squared. 30 seconds. See if you guys can figure out these 3 and check with your answers. Check your answers with your neighbors. Together. What do we say for the first one? Anybody say -16? Good, it's positive. Because this one means -4 times itself, right? So that is 16. That's correct. The next one is the one that throws a lot of people off. Positive 16 or -16? And we have people that very firmly believe opposite answers here. We do exponents first, and that's the key. That's the key. A lot of people look at that and say, oh, it's -4, and -4 is being squared. But exponents, by virtue of having to come like pretty early in the order of operations, right? First parentheses, you guys remember PEMDAS, right? Parentheses, then exponents, then multiplication, division, then addition, subtraction. By virtue of exponents coming very high in the list, it means that exponents are fairly weak in terms of their reach. I don't know if you ever thought about exponents being weak or strong, but I'm going to tell you that they are weak. That exponent right there is not strong enough to reach all the way out to that negative sign. The exponent is weak, and it only applies to what it is physically touching. In this case, it is touching the number 4, and the negative sign is sitting way out in the front. And if you need another reason to believe why that's so, would you guys agree that having a negative something is really like taking -1 and multiplying it by that something? So we usually wouldn't write it that way, but there's an implied multiplication in this problem. And so which comes first, the exponent or the multiplication? Is the exponent, and the multiplication is just hanging out. And so this is really -1 times, and then 4 squared is 16. And so this answer is -16. Really, really common mistake. Okay, and then the last one, yeah, this one is negative because we've already done this part, and we know that the answer to this part is positive 16, right? And then that negative sign is just copied in the front. Okay? All right, so the activities start on the next page. I want to say one last thing about these laws of exponents. If you are ever at a moment where you are not 100% sure about which of these properties you should use, just plug some numbers in. Just make up some small, simple arithmetic problem similar to the ones that we saw in this big chart on the previous page, and you will figure out what the property is, as opposed to just blindly guessing, oh, I think we're supposed to multiply those exponents, or I think we subtract them. Make something up, figure out the rule, and then proceed.